Anyways, I am now making a recording of everything on my phone. After class, I will get that onto YouTube for you. I apologize that that first section has been lost, but my computer keeps giving me this something went wrong, try to reconnect error every time I do it, and I don't know what's up with that. So the idea is that, yeah, the procedure for integrating using partial fractions, we've got a rational function. First, we factor the denominator, factor what's on the bottom. We write out the form of the partial fraction decomposition, so we'll have a over this, b over this, c over this. We multiply both sides by the LCD to get a polynomial on one side, a polynomial on the other. We find the coefficients, figure out what a is, what b is, and what c is, and then integrate each guy separately. Each of those fractions that we have in that decomposition, we integrate each one separately. So I'm going to do two examples of this, and then I'm going to give you folks a break. So the first example here, we have x cubed minus 2x minus 1 over x cubed minus x dx. Plus? Plus, yes, thank you. So the first thing to mention is that we're going to want to factor the denominator of this. So we can factor out an x, that we have left with an x squared minus 1. And x squared minus 1 will factor as x minus 1 times x plus 1. So that's how that guy is going to factor. So now that I factored it, I can go over here and I can do the partial fraction decomposition. So I start by writing out, oh great, that's supposed to be an x squared. Sorry, not an x cubed. If it was an x cubed, I'd have to use a completely different method to deal with it. Yeah. So x squared plus 2x minus 1 over that thing, x minus 1, x plus 1 is going to be something over x plus something over x minus 1 plus something over x plus 1. So first we're going to multiply both sides by that least common denominator to clear the denominators. On the left, we'll get x squared plus 2x minus 1. In the a term, the x's are going to be canceled. I'll be left with a, x minus 1, x plus 1. In the b term, the x minus 1s will cancel. I'm left with b times x plus 1. And the c term, the x plus 1s are cancel. I'll be left with c times x minus 1. And then I've got to get this equation, I've got to find a, b, and c. This one's going to be an easy one that I can do by just plugging in different values for x. So if I plug in x equals 0, the left-hand side will just become a negative 1. The right-hand side, this will become negative 1 times positive 1, which is negative 1. So I'll have negative a. And the b term and the c term will both become 0, because they'll both have x's in them. If I plug in x equals 0, this will be 0, this will be 0. So negative 1 is a, so a is 1. Now if I plug in x equals 1, the left-hand side is 1 squared plus 2 times 1 minus 1, which is 2. Here, this a term is 0, because there's x minus 1 in it. When I plug in x equals 1, it goes to 0. Here, this b term is b times 1 times 2. So we have 2b. Here, the c term is c times 1 times 0, which is 0. So 2 is 2b, so b is 1. And if we plug in x, it's negative 1. On the left-hand side, negative 1 squared is 1. 1 minus plus 2 times negative 1 is 1 minus 1 minus 2 minus 1 gives you negative 2. Here, if I plug in x equals negative 1 here, this x plus 1 will be 0, so we get a 0 here. This x plus 1 will be 0, so we get a 0 here. Here we have a negative 1 and a negative 2. Negative 1 times negative 2 is 2. So we have negative 2 is 2c, so c is negative 1. So we found what a, b, and c are, which means we now know how this thing inside the integral splits up. A is 1, so there's a 1 over x. B is 1, So there's a 1 over x minus 1. C is negative 1, so it's a negative 1 over x plus 1. Right? So now we've taken that complicated rational function, split it up into three simple ones. There's a 1 over x minus 1, negative 1 over x plus 1. And that's using the a, b, and c that we found. To finish, we just need to integrate those three guys. 1 over x integrates to ln absolute value of x. 1 over x minus 1 integrates to ln of absolute value of x minus 1. And negative 1 over x plus 1 integrates to negative ln absolute value of x plus 1. Again, you could do those using substitution, those second two using substitution if you wanted, but you can also easily do it just using those formulas that I mentioned in the first slide. So this is what an integral using partial fractions looks like. Right, you take the function, you factor the denominator, you figure out what the form of the decomposition is, multiply both sides to clear denominators, find the a, b, and c, do the integral. I think I'm going to give you a break now and do this example 4 after the break, and then move into the more complicated ones after that. But anyways, it's just sort of one example of what partial fractions looks like. Take a 10-minute break. At 12:45, I'll get into another example and move on from there. Oh, I don't have it with me. I have it at my office, so you come after class. Sure. Yeah. Oh, maybe I do. So I realized I saw some papers in here.
I want to see a little trick here.
Oh, sorry. The new assignment. Oh, the new one. Yes. Sorry. Oh boy, where was that? Okay, these are all quizzes. Some more extra quizzes, answer keys. It went around the class. Check in the back of the class.
You take any function.
Yes, it's in my office. So if you go to my office, then yes, you grab it. Yeah. Just find me after class. Oh. Anyone else not get the written assignment?
So if you take
Seconds.
Well, that's one thing out of the book here. You can check.
But it's not the form, it's because of the factors. Here we have an x squared plus 4, right? That's why we have an x squared plus 3. X squared plus x plus 3. Yeah. So we're using the same formula both times, right? So here we have an x squared, that's why we have an x, we also have an x squared.
It can be a bit complicated, but most of the time, you know, like,
right? If we had, for example,
if it's a definite integral
plus 8, that's plus 2.
if it's an indefinite integral, then
minus
it's a
2x plus 3.
So let's do.
So I don't remember the cubic factor. Anyway, so this guy would be a factor. And that's why, so then there's like, it's only the x, this, but x squared plus something, that's a 10 factor. And that's why you have to worry about that situation. You don't have to worry about x because those are no zeros. Does that make sense? Yeah. Okay. Sorry, I have to go to the bathroom.
So this is just that would be the definite integral here. So just check it on your calculator. take the function that was originally given to you, and you put this into your graphic. So you x second dx to the negative 3x graph it. Now, what you want to do for an indefinite interval, if this was a definite interval, you would evaluate that, right? And you would get a whole bunch of random stuff, right? So, let's say you want to check from 1 to 2. So, I see what this is right here. We're creating this whole thing. Negative 6 over 3 minus 1 over 9, so then negative 6 and then minus negative But anyways, so what you would do is you would plug that number into your calculator.
Oh, the next week, it'll be due. I'll make it do it Thursday.
Okay.
Yeah. Because I was gonna say there's no class. I can't do it. I don't want to do it on Tuesday because Tuesday is actually the holiday.
Yeah.
So I was trying to decide between Wednesday and Thursday. I'm like, there's no reason to have it do on Wednesday instead of Thursday. I'll do it Thursday. Yeah.
So I chose the limit of 1 to 2. So it has to be the lower limit, upper limit. Tells you the decimal approximation. Your decimal approximation is your answer is correct.
I don't know why repeated factors
So
happen once and then twice.
And then twice. Okay. The reason they have to occur twice is because if you don't, you won't have enough letters. You always need the same number of letters as the degree of the denominator. I think I mentioned that last class.
I know, I just thought I want to use repeated factors to make it like say x
Like x plus 2 and x plus 2 twice. Well, then you've got the same thing more than once.
Right. I know what you're saying is true, but it's counterintuitive.
Like if you put this and you put this, what would happen is there'd be no way to tell which one was B and which one was C. You would actually end up with an equation. Actually, if I kept doing this, I ended up with this situation. Now, what would happen if I plugged in x equals 1? Well, then I'd actually get a 2b here and a 2c. And there'd be no way to find B or C separately.
Yeah, it's just hard to persuade me that it's true that it's going to turn out equal.
Yeah, and then the other thing will happen, if you plug in -1, all 3 terms will now go away. And I'll get -2 equals 0.
I was trying to do it just with.
And it won't work. Yeah, so the reason is if you did it like this, you kept going, you'd end up with much bigger problems later on.
Okay. Yeah.
That's
I was trying to do this with just agree 2 fractions, like
oh yeah,
2/3
yeah,
and 1/9, just for comprehension. And then I did, how am I going to find A, B, and C? So yeah, this is, it all looks obvious after you show it.
Yeah, so there's just some weird formulas like one with trapezoidal, like I don't know. And stuff like that. And then Simpson too. So I've went over a lot of random calculus and math books prior to doing courses, so just like my dad's whole text.
Can I have my dad's old checkbook too? Like that.
Like mine's from like 1960 or 1970, but yeah.
Yeah, so mine.
But yeah, I've just done a lot of random stuff, and like a friend of mine told me that matrices were super helpful in a few courses, so he recommended that. That was fun.
Which I was gonna say they are really helpful
Like
in
physics.
I was gonna say if linear algebra was a prerequisite, I would so be like, yeah, just do it this way. Your calculator could do it for you. But it's because I know, yeah.
I bombed that when I tried it, but I'm gonna try it again.
Yeah.
It's my midlife crisis.
Linear algebra.
Yeah, I gotta go back and defeat that thing. It pissed me off so bad. But yeah, my dad texted too, and he died in 71.
Okay. I'm going to move on to example 4. I've got a fair bit more to get through before the end of class today. It has been 10 minutes. There are some people who are not back yet, but I'm going to get started anyways, and they can catch up to the video if they need to.
It's part of the.
So example 4, here we have an integral that looks like x squared minus 2x plus 1 all over x minus 1 squared x squared plus 1. Now the good news about this integral is it is already factored, right? You can't factor x squared plus 1 any further. X squared minus 1 does factor. Is x minus 1 to x plus 1? X squared plus 1 you can't factor. So you can't go any further with this guy. So instead, what I'm going to do here is, well, sorry, you can't set factor any further. So what I'm going to do here is, again, I'm going to start by writing out the partial fraction decomposition. So this guy, x squared minus 2x minus 1 over x minus 1 squared x squared plus 1, it's going to split up as something over x minus 1, something else over x minus 1 squared, and something x plus something else over x squared plus 1. All right, that's what the form of this decomposition is going to look like. So again, I multiply both sides by the denominator here to clear the denominators. By the way, the reason this form of the decompositions work, right? If you have something squared, you've got to have something over that thing. You've also got to have something over that thing squared. You have a factor with an x squared in it. That's when you need the cx plus d. That's when you need two different letters, one in front of x. And those are those rules that were on that slide at the beginning of class that I said, I'm not going to go over them again, but they're there. So, again, multiply both sides to clear denominators. Here I'll get x squared minus 2x plus 1. On the right-hand side, one of the x minus 1s is going to cancel in the a term. So we'll get ax minus 1x squared plus 1. The x minus 1 squared is going to cancel in the b term. So I'll get b times x squared plus 1. And the c term, the x squared plus 1 is going to cancel. So I get cx plus d times x minus 1 squared. So now this is one, again, if I try plugging in the different values for x, trying to make it work, I'll get stuck with the fact that I can't make the x squared plus 1 go to 0. So this is another one I'm going to do by actually expanding both sides. So the left-hand side is already expanded. If I expand the right-hand side, x times x squared is x cubed. So I'll have an ax cubed. Negative 1 times x squared is negative 1. So I have a negative ax squared. X times 1 is positive 1, so I'll have a plus ax. Negative 1 times positive 1 gives you minus a. Here I'll have a bx squared plus b. And for this one, I'm actually just going to write it out like this for now. Cx plus d, x minus 1 squared will expand as x squared minus 2x plus 1. So this whole thing on the end will become a cx cubed minus 2cx. No, cx cubed minus 2cx squared plus cx plus dx squared minus 2dx plus d. So you'll notice when I've expanded this, it's gotten really long and annoying. And one of the things that happens when you, I'm going to keep going, and I'm going to do the correct like term things, and then I'm going to talk about how I'm going to deal with this situation. So x cubed terms, there's an a and there's a c. So we have a plus c times x cubed. If we look at the x squared terms, we have a negative a, we have a positive b, we have a minus 2c, and we have a positive d. So we've got a negative a plus b minus 2c plus d x squared. If you look at the x terms, you've got a positive ax, you've got a positive cx, you've got a minus 2dx. And if you look at the terms with no constants, we have a negative a positive b, and a positive d. Plus negative a plus b plus d. And this, again, is one of these situations you look at it, you're going, this is really daunting. I am not entirely sure how to approach this. And one of the ways we can actually approach this is actually going back and saying, okay, I did say there was one thing I could have plugged in that would have helped us solve that. And that was plugging in b equals 1. If I had plugged in b equals 1, this thing would have gotten simpler. So let's go back and do, or sorry, x equals 1. If you plug in x equals 1, it would have made the whole thing simpler. Let's go back, let's plug in the x equals 1, let's see what information it gives us, and then we can go back and just continue working on this part. So if we plug in x equals 1, the left-hand side will become 1 squared minus 2 minus 1, which is negative 2. The right-hand side will become 0 for the a term. The b term will become a 2b. And the c term, the cx plus d term will also become a 0. So that tells me that b is negative 1. And again, that's not helping me a lot, but it's helping me a little bit. It does tell me a little bit more about here. So this plus b here can become a minus 1. And this plus b here can become a minus 1. Okay. Now the other thing I'm going to do here is I'm going to look at the coefficients here, look at the coefficients here, and actually write out the equations I get them. So there's no x cubed here. There's an a plus cx cubed here, which means that a plus c is 0. There's 1x squared here. There's this many x squareds here. So negative a minus 1 minus 2c plus d equals 1. There's minus 2 x's here. There's this many x's here. So a plus c minus 2d equals minus 2. There's negative 1 constant term over here. There's negative a minus 1 plus d over here. So negative a minus 1 plus d is negative 1. So, if I want to solve this thing, the first thing I'm going to notice is here it says that a plus c is 0. Here I have an a plus c here, right? So if a plus c is 0, here that a plus c is going to tell you that 0 minus 2d is negative 2, which means that d is 1. So now I know what d is. And now if I go down here, negative a minus 1 plus d is negative 1. I know that d is 1. Negative a minus 1 plus 1 is negative 1. That gives me that negative a is negative 1. So that tells me that a is 1. And then if I want to figure out what c is, so I know what b is, right? I've used a plug in 1 to find what b is. I know what d is. I know what a is. If I want to find what c is, I use the fact that a plus c is 0. And so we have 1 plus c is 0, so c is negative 1. Now this is sort of a very creative approach to solving the system of equations. It's not systematic at all. Sometimes the easiest way to do these sorts of things is just sort of finding a creative approach. Looking at the equations, saying, okay, here's a similarity, here a plus c is 0, here a plus c also has to be 0. And then using the fact that I already know that b is negative 1 and such. There isn't always a system. Well, there is a systematic way of dealing with it. It's really long and complicated, requires matrices. And by the way, if something like this came up on a test, there would be a hint involved that would say, here's your equations. If you have this, plug this one into this one, or something like that. I probably actually just wouldn't give you something that's complicated on the test in terms of the amount of time it takes to do. This is more the difficulty of something that's going to come up on that written assignment that I just handed out. Test wouldn't do this. Okay, so now I know what A, B, C, and D all are. So, A here is 1. So I've got, what I'm trying to integrate, I've got a 1 over x minus 1. B is negative 1. So I've got a negative 1 over x minus 1 squared. C is negative 1. Oh boy, I'm going to have to erase a little bit. I'm going to have to erase this part where I found D. C is negative 1. So I have a negative 1x, and D is positive 1 over x squared plus 1. Now that first guy, negative 1 over x minus 1, that just integrates to ln of the absolute value of x minus 1. Right? I sort of mentioned that before. That's one of your rules for how you integrate these things. Here, 1 over x minus 1 squared, well, that's x minus 1 squared to the negative 2. If you do the substitution, u equals x minus 1, you integrate it, you will get 1 over x minus 1 as the antiderivative. That's using that second rule. If we have a number over ax plus b to a power of n, the power is always going to get 1 smaller. There's always going to be, you're always going to have to divide by whatever the new power is. Here the new power is negative 1, and dividing by negative 1 will turn that negative sign into a positive sign. Now, annoyingly, for this part, we're going to have to still do some more work. We're still going to have to split it up into 2 separate integrals. Here I have something x plus something over x plus 1, x squared plus 1. And I'm going to have to write it as one integral, which will be negative 1x over x squared plus 1. And another integral, which is going to be 1 over x squared plus 1. This first one, we can integrate using a substitution, u equals x squared plus 1. If we do that, the du will be 2x. Here we don't have 2x, we have negative 1x. So we're going to have a half of ln absolute value of x squared plus 1. Again, if you look at that formula I gave on this first slide in this section, that was there. And this guy is just arctan, right? 1 over x squared plus 1, that's just the derivative of arctan. So this integrates to tan inverse of x. So the final answer here will be ln absolute value of x minus 1 plus 1 over x minus 1 minus a half ln absolute value of x squared plus 1 plus tan inverse of x plus c. So that's what this solution to this sort of problem looks like. Yes?
When we were first setting up the fraction decomposition,
Yeah.
how exactly did we get the cx plus d over
X squared plus 1. We have a factor of x squared plus 1. Whenever we have a factor which has an x squared in it that you can't factor any farther, you always need something times x plus something else on the top. That's one of the rules. The reason is because you need to have the same number of letters as the degree of the bottom. And this has degree 2, so you need 2 letters for it. And because you can't factor any farther, you can't have like 2 separate factors for those 2 letters. So one of the letters you're going to have to multiply by x. Yeah.
So if it was an x to 3 plus 1.
Then you factor it. X to 3 plus 1 factors x plus 1 times x squared minus x plus 1. Right? The sum of cubes, there is a way of factoring that. Something squared plus something you can't, and that's why you've got to do it this way. But yeah, if it was x cubed plus 1, you could actually factor it farther. Yeah. I probably wouldn't even ask you to factor that, but yeah. Okay. So there's 2 more things I need to cover in section 7.4. The first one is long division of polynomials. Now, is there anyone here who never learned this in high school? Long division of polynomials. Okay, there are some people who never learned. Anyways, it's supposed to be part of the high school curriculum. I know there's some people who, maybe never learned this. How many people here remember how to do this from high school? Okay, I see most people don't. So I'm going to go over it again and sort of just give you a quick refresher on how you do this. The idea is I mentioned before that partial fraction decomposition works as long as the degree of the top is smaller than the degree of the bottom. If we have the degree of the top being bigger than the degree of the bottom, or if they're the same, you're going to have to use another technique, which is called long division of polynomials. It turns out to actually be easier than partial fractions, The only annoying thing about it is sometimes you still need to do partial fractions after you do long division of polynomials. But anyways, I'm going to go over this. So long division of polynomials is a procedure which is necessary for integrating rational functions if the degree of the numerator is higher than or equal to the degree of the denominator. So if the degree of the top is bigger than, or if they're the same, you have to do this. You have to do long division of polynomials first. So the procedure for long division is called divide, multiply, subtract, bring down. So I'm going to sort of explain these 4 steps through an example. This is example 5 now. And the example looks like this. Here we're trying to divide x cubed plus 2x squared minus 3x plus 4. We're trying to divide it by x minus 3. So we're trying to put x minus 3 into x cubed plus 2x squared minus 3x plus 4. So the first thing we ask ourselves is the divide step. We want to divide the biggest term here by the biggest term here. X cubed divided by x is x squared. So we put an x squared on top. Second step is multiply. This x squared that we got up top, we multiply by x squared, x minus 3. X squared times x is x cubed. X squared times negative 3 is minus 3x squared. So again, first step, divide the x cubed by the x. We get x squared. Second step, multiply. X squared times x minus 3 gives you x cubed minus 3x squared. Third step is subtract. We take this guy minus this guy. X cubed minus x cubed gives you 0. 2x squared minus negative 3x squared gives you 5x squared. And then we're going to bring down the next term. The next term here is negative 3x. And repeat the procedure. So we divide again. 5x squared divided by x gives you 5x. Right? One of the x's will cancel and get up to 5x. Then we do 5x times x minus 3. 5x times x is 5x squared. 5x times negative 3 is minus 15x. Then we subtract again. 5x squared minus 5x squared, they cancel. Negative 3x minus negative 15x becomes 12x. And then we bring down the next term, plus 4. And then we repeat again. X goes into 12x, or 12x divided by x is 12. Right? 12 times x minus 3 is 12x. 12 times negative 3 is negative 36. Subtract. And if we subtract, 12 minus 12 is 0. 4 minus negative 36 is 40. So this thing here is called the remainder. The remainder here is 40. So what this says is that this big polynomial is the little one times the quotient plus the remainder. The big one is x minus 3 times this plus 40. There's 40 left over. That's in the big one. That's not in this times this. Okay. Any questions about this procedure at this point? Any steps that people didn't get? There's going to be a couple more examples I'm going to do. The other examples I'm going to do are going to be examples that are in the context of actually doing integrals. So I'm going to do this part of it a little bit faster. If you're having difficulty with this part, again, check out the test stuff that's in the textbook. Look up your grade 12 stuff if you need to look it up there. Okay. I'm just going to talk a little bit about how we use long division of polynomials to do integrals. If you remember at one point, I did this example. Or something, it was something like that. Or maybe it was 2x squared plus 3. And I was trying to integrate this thing. Or this is like the first class. And I remember everyone was like, oh, I don't know how to do this. I don't know how to do this. It turns out the trick was to write it like this. Right, say x squared plus 3 is 2 times the bottom plus a number here. This thing here, what I'm actually doing there is I'm doing long division of polynomials. The bottom goes into the top 2 times, and the remainder is 1. So if you remember, the next step I said is, okay, well, you can split this up as 2 separate things. It's going to be 2 times this over this, which just gives you 2. And then it's going to be 1 over that thing. Right? And so the way we're going to use long division of polynomials to do integrals is the same way that we did this problem back on the first day of class. The long division of polynomials allows us to write the top as something times the bottom plus another number. And that something there, this thing that's called the quotient, is always going to be left on its own. The thing that's left over times the bottom is always going to be left. The remainder is going to be left over the bottom still. So, long division of polynomials allows us to express a rational function as a polynomial quotient, as whatever the quotient is that you got, plus a remainder over the original divisor. So whatever the remainder is, that's still going to be over whatever the original denominator was. Well, original denominator, sorry, not original divisor. Well, divisor is the denominator, but. So, this is what an example of this is going to look like. So example 6, we have the integral of 3t minus 2 over t plus 1. And the key thing is, before we go any farther, we need to do long division of polynomials. We need to take t plus 1 and we need to divide it into 3t minus 2. And if we do this, we ask how many times does t go into 3t? It goes in 3 times, or 3t divided by t is 3. Multiply, 3 times t is 3t, 3 times 1 is 3. Subtract, negative 2 minus 3 is negative 5. And we don't have to worry about bringing anything down. So there's nothing left to bring down. What that means is that this thing can be written as, whatever the quotient was, 3 plus the remainder, which is negative 5, over t plus 1. That's basically what this long division of polynomials has told us. That 3t minus 2 over t plus 1 can be written as just 3 plus negative 5 over t plus 1. If you're not convinced of this, just do the algebra to simplify this thing. The 3 is 3 times t plus 1 over t plus 1. The 3 times t plus 1 will give you 3t plus 3. 3t plus 3 plus negative 5 gives you 3t minus 2. So if you do the algebra, this thing and this thing are the same. But where the numbers in this thing came from was from the long division. But now that I've done this, so firstly, the thing to mention, this guy here I couldn't integrate. There's no quotient rule for integration, so I couldn't do anything with this guy originally. But these two are both things I can integrate. The antiderivative of 3 is just 3t. The antiderivative of this guy is negative 5 ln absolute value of t plus 1. Again, that's sort of one of those rules. The negative 5 is just a constant. It stays in front. 1 over a linear thing, like t plus 1, t plus 2, t minus 3, is ln of absolute value of that linear thing. So the idea is that by doing a long division of polynomials, I can split this up into pieces that can be integrated. And here's another example that I'm going to do using long division of polynomials. Here we have, so any questions about example 6 here before I move to example 7? Okay. So example 7 here, I have the integral from 0 to 1, x cubed minus 4x minus 10 over x squared minus x minus 6 dx. So here, the degree of the top is bigger than the degree of the bottom. So I'm always going to start with long division of polynomials as long as the degree of the top is larger than or the same as the degree of the bottom. So long division of polynomials is going to look like this. I don't know if you remember this, but when you do long division of polynomials and there's a term missing, always write it in as a 0. So, first thing we ask, x cubed divided by x squared. That gives you just an x. Then we do x times this whole thing. X times x squared is x cubed. X times negative x is negative x squared. X times 6 is negative 6x. We then subtract. X cubed minus x cubed gives you 0. 0 minus negative x squared gives you x squared. Negative 4x minus negative 6x gives you 2x. Bring down the next term. Then we repeat the procedure. X squared divided by x squared gives you 1. 1 times this thing is just that thing. X squared minus x minus 6. We subtract again. X squared minus x squared is 0. 2x minus negative x is 3x. Negative 10 minus negative 6 is minus 4. And so what happens in example 7 is that the long division of polynomials allows us to write that integral as the integral from 0 to 1 of what the quotient is. The quotient there is x plus 1 plus the remainder, which is 3x minus 4, over the original denominator. So long division of polynomials allows us to write the thing we got like that. X plus 1, that's something that's very easy for us to integrate. It's just a polynomial. But this guy here, we can't integrate directly. This guy here, we're going to have to integrate using partial fractions. So again, there are some questions like this example 7 here where we have to do both long division of polynomials and partial fractions to get to the answer. So when I do the partial fractions here, the first thing to mention, x squared minus x minus 6 factors is x minus 3 times x plus 2. Right? First thing to mention, that's how this guy factors. So 3x minus 4 over this thing, x minus 3, x plus 2, is going to be something over x minus 3 plus something else over x plus 2. And we need to find what the a and the b are. So we multiply both sides by the denominator to cancel out. We get 3x minus 4 is a times x plus 2 plus b times x minus 3. And then we need to plug in different values of x to find a and b. If x is negative 2, 3 times negative 2 is negative 6. Negative 6 minus 4 is negative 10. A times negative 2 is 0. Negative 2 minus 3 is negative 5. So negative 10 is negative 5b. We plug in x equals negative 2. Divide both sides by negative 5. B is 2. Now if we do the same thing, but instead plug in x equals 3, 3x minus 4 is 9 minus 4, which is 5. A times 3 plus 2 is 5a. 3 minus 3 is 0. 0b is just 0. So 5 is 5a, so a is 1. So now we know how to split up this complicated rational function into two simpler ones. So to finish off this example, we have the integral from 0 to 1, x plus 1 plus a is 1. So we have 1 over x minus 3, and b is 2. 2 over x plus 2. And then we just need to integrate. Antiderivative of x, x squared over 2. Antiderivative of 1 is x. Antiderivative of 1 over x minus 3 is ln of absolute value of x minus 3. Antiderivative of 2 over x minus 2 is 2 ln absolute value of x plus 2. And now we need to do this integral from 0 to 1. It's a definite integral. Plug in 1, we get 1/2 plus 1 plus